the value of pi that you will get has an accuracy of 11 decimal places. So Leibniz series would have involved millions of terms to get that kind of an accuracy. So this has been explained to you twice or thrice already. This is in the Bhuta Sankhya notation. This is taken from Nilakantha's Aryabhatiya Bhashya. It's often said that the Kerala astronomy was all limited to Kerala, and they were writing not for Kerala alone. Of course, they are writing in Malayalam and all that. Nilakantha, whenever he is writing in Sanskrit, he never uses Katapayadi except for indicating his date of birth. Everywhere he is using Bhuta Sankhya. This is the all India way of this thing. Whereas if you go to Kannada, there are many texts where only everything is done in Katapayadi only. Katapayadi was not that widely known, at least in the rest of India, at that period. Whereas it was known very well in South India. It was used in Tanjavur in Carnatic music. Katapayadi is a very common thing. That's where most people learn Katapayadi, not in mathematics but in music. A lot of things are encoded in Katapayadi there. So that was in Tanjavur, which is far away from Kerala. But Nilakantha is writing everything, as you notice, in Bhuta Sankhya. So, if you go take this argument further, do the same argument that they are doing, what I think over, so that can be rewritten. In fact, the first term itself is explained there. To it you add 1 over something is already there explained in the denominator in Yukti Bhasha. So to that you add 1 over something and try to calculate, then this will be the kind of next term. Then you go further, this will be the kind of next term. Madhava thing will come up to this. Madhava's first correction is this much. Madhava's second correction is up to this much. 320. So the next term will be 6 squared. And you can clearly see that there is a continued fraction network. There is an old story that Professor Madhava went to Ramanujan's room in Cambridge and he was telling him some problem about the door numbers in a street from which he came. And then Ramanujan said, I don't understand how. So Ramanujan gave an answer. And then Madhava asked him, how did you do it? So Ramanujan said, by continued fraction. I knew the moment I saw that there must be some continued fraction involved. So this continued fraction is a very old thing. From the time of Puttaka, this is what Indians are repeatedly doing. That re-express. Now, about 200 years later, there is a continued fraction for pi. This is obtained by Brownker from this Wallis product formula. He converts it into it. It first appears in the textbook that Wallis wrote called Arithmetica Infinitorum in 1656. This was the book that influenced Newton to begin his calculus. This had many elements of calculus. So this is the Brownker continued fraction. This is different from this. This is 1 3 squared, 1 squared, 3 squared, 5 squared. This 1 squared, 2 squared, 3 squared. That's the kind of result. This I put it on the buster. This correction I put on the buster. But better always put it after S terms. Then you will see the power of this continued fraction. If you put it on the first term, you are almost starting from nothing and wanting to get pi. Then you have to go quite far away in the series to get a good approximation. This is just to show the beauty of the approximations that Madhava is doing. Next thing you can do is, this is done in Yukti Bhasha and done by Madhava. Now in this formula, you have an expression for 1 by AT, right? Now what you do is, you convert your Madhava series itself in terms of those divisors. So what is that? You have 1 minus 1/3 plus 1/5. But you write it as 1 minus 1 by A1 plus 1 by A1 plus 1 by A3 minus 1 by 3 minus of 1 by A3 plus 1 by A5 minus of 1 by 5. Doing this, the reason it is done is this A1 and A3 are so chosen that this sum minus 1 by 3 will become a very beautiful expression. By the argument of closeness of that correction divisor to the exact result, you have something called the Staulia, and from that argument, this combination has always a beautiful form whenever you have those particular specified A1, A2, A3 that Madhava had given. He had given 2 of them. So if you put the first of them, you will get this series. So this is a transformation of the Leibniz series that Madhava does.
Why do you call it a Leibniz series? Objective.
Madhava is mixing.
No, but you put bracket. Instead of that, you put
No, once it becomes common nomenclature, one doesn't need to. But still, one has to remember that they have come in different times and everybody is talking. But that's a different thing.
you should have
You are right.
no, if he
There is nothing proper about this. I was only raising a question. What is the logic? I am not saying that I have done something.
Let us have a common listening.
if
So-called Leibniz.
I think I and you cannot decide this. This has to be decided by larger consensus. Just me and you deciding, we can decide to call it anything. Then larger consensus are arrived by lot of fight and lot of argument.
Saying
but
so-called.
you are yourself a historian mathematics, so you can call it.
By saying so-called.
No, always
You are not saying
no, always-
Leibniz, no.
This is how I have written this. At that point, we have to indicate that series everybody knows in this name. That's about. So this is the next series that we obtained by using this correction divisor. First correction divisor that we saw. P plus 1 by 2 by P plus 1 squared by 1. As a divisor, this will look like P plus 1 squared by plus 1 by P plus 1 by 2. 1 over Kp. That's how this is. So if we use this, we will obtain. So you get a series like this. So these differences will give rise to this kind of term. So now you can see these are going like cubes of odd powers. Already the series is becoming faster. Now, if we, this is the zeroth order. This is not even Madhava's divisor. You just use 1 over P plus 2P plus 2 as the divisor. Not even the complex thing. Okay. I'll come back. What Madhava is giving here is the correction term, which is already the second term in this continued fraction. 1 over 2p plus 2 is the first term that will appear in that argument. The next thing that will appear is this much. That is what Madhava is giving as the first correction. This is Madhava's first correction. Madhava's second correction is this. That will appear by taking up to this point, up to this point. Now the transform series first is given with this correction 1 over 2p plus 2. That is this. Now we use 1 over the next correction of Madhava, which is in the continued fraction terms. If we use this correction, which is the first order correction of Madhava, we get a series with the fifth powers of odd numbers again. Now, Yuktibhaja and Krimakari do not discuss the transform series when we use the second correction divisor given by Madhava. This which goes all the way up to here, up to 4 square. The correction divisor is given by Madhava. This is the correction divisor given by Madhava, which is called the more accurate one. No, not this one. This is the more accurate one. So for this has this much times of this correction divisor. If we use that, we will get the 7th powers of odd numbers. Like that it will go on. So quickly to place this work of Madhava in the history of the geometry of circles. Print Fabulous has 3.16, Babylon has 3.125. This is taken from this Borrain and others have written the source book of Pi, one of the very nice books written in around 1899. Gregory, who is a scholar of Islamic mathematics, Borrain is one of the important persons involved in computing Pi 2 in modern days by powerful methods. Jaina texts always use root 10.
Sutra says 3.1.
How?
No decimal places.
No, that's all. Archimedes has this inequality. Then Ptolemy has this recurring decimal. It's a, this number is a, this 17 by 120 is a, done in the base of 60. Then Dewey, then this person's date is not very certain, but he is one of the earliest persons to give this 355 by 130, which is 6 decimals. Aryabhatta is 4 decimals. Now suddenly when you come to Madhava, you see a jump. You have this 11 decimals. So before that, the 355 by 130 would have been the most accurate. Now, it's not necessarily just enough to know that you have some formula which is accurate. You should know the level up to which it is accurate also. So you should have an angle to a better approximation to know that this is a good enough approximation. Otherwise, you can throw some number and say somebody had an approximation. Al-Kashi did by computation up to 2 to the power 6 into 2 to the power 27 side. He is one of the greatest calculators of the 15th century in Maraga, in Samarkand area. 16 decimal place. Now the first exact expression starts coming around the time of K, but he uses polygon doubling only to calculate. So the first person to use infinite series apart from Madhava is Isaac Newton in 1665. He spends 3 months or something in one summer or something to calculate. By then he has seen this Walid's product, Bunker's continued fraction are available. So it tries to obtain some kind of an infinite series for the related quantity and calculate. Sharp's series is for tan inverse 1 by 1 over root 3, which is the Madhava's Chapikarana series. So that would give him 71. Then a different way of computing pi started with this kind of an expression of John Martin. We will come to Ramanujan next. So let us look at these exact expressions. So first exact expression is by Madhava. All these series are there. To some extent, even the continued fraction can be thought of as Madhava's by the kind of argument that Divasha is giving. The idea has this, which is purely trigonometrical. You can go on approximating the area of a circle by that will give you this nested square roots. Wallis had this infinite product, which is also obtained from this trigonometry only. Broncker converted that into this continued fraction. Newton had this more complex series. So Gregory series is in 1671, Leibniz series is in 1674, Sharp series is 1699. All these are found here.
Newton series is based on what?
It's related, he is integrating something and doing it. He doesn't integrate, what he does is takes a power series and
Not 1 over 1 plus x square.
No, it's not based on it's Leibniz who does that kind of. This tan inverse x is integrated by Leibniz, and Gregory does it in an independent way. Leibniz has a way of integrating that to find the arc of a circle. Newton is a computer. He has some infinite series. He can invert it by computation. He can see patterns in first 3-4 turns, but he doesn't have analytical arguments at that time. He doesn't have an exact expression. Even Sine x.
No, all the thing is that it is only by reversing.
And he doesn't have exact expression even for Sine x as a proof. No, today you can think, you should see how it would have been written in Gregory's time. I think Leibniz himself worked it out independently of Gregory. That's my understanding. I am not an expert on this subject, so there are several books written on this. These issues can be, if you spend some time, if you have a question, you can definitely know much more about it. I don't think there was that kind of communication. Gregory is a Scotsman, and I don't think even Newton knew then it's communicated in a long paper. There is a huge paper by Whiteside in Archive of History of Exact Sciences written in early 60s on this Gregory Newton. So Ramanujan in his paper of 1914, this goes back to his ideas in 1910. Even Hardy writes that this paper is based upon Ramanujan's work in India. So he calls what is called modular equations and phi. So let us look at it. So one of Ramanujan's earlier papers is called modular equations and approximations to phi. It was published later from London in 1914. He goes to London in March of 1914. And then this appears in the Quarterly Journal of Mathematics. I think second or third paper to appear in India. And there are several, this is the 43rd, 44th series in that. So there are various results like this. And Ramanujan himself thought that this was a very, very powerful one. He notes the loss is extremely rapid. Now, what happens is in 1990s, in 1985, Gosper uses this series This is the same series as the one common set very fast. To get a good computational algorithm, and he was able to go to 17 million. I mean, there are millions of people in between. In between 100 and 17 million, it's not a jump like that. I'm just coming. There are lots of people who calculated, find great amount of energy came out of that. The current thing seems to be around 5 trillion. I mean, this must have changed by then now. That's number. And it's usually said, I think if you have pi up to 11 decimal places or 10 decimal places, you will make only an error of 1 foot in calculating the circumference of Earth or something like that. So, what will be the practical utility of having much higher things is as much of theory can be taken. Now we will go to Madhava series for phi. So these are just definitions. This is an arc, this is the shala, this is the ja, and this is the chapa. This arc is the chapa, this is the ja, this is the shala of this arc. And this is the koti. This is kotijya. This is bahujya or ja. And this is shala or kramajya. So one is r sin theta, one is r cos theta, another is 1 minus r cos theta. So now series is to be obtained for this. Now the main methodology is again divide the arc into n parts and calculate. To calculate, you need some formula for differences of sines and cosines for various points. So these were worked out, as I mentioned even in the beginning, these were worked out by Aryabhatta. Essentially this formula in some form is due to Aryabhatta. This coefficient he might not have had exactly in his statement, he is giving an approximate value. Nilakantha in his explanation of Aryabhatta's work, he is writing it, but many other people are also sort of obtaining it, that the sign difference of two signs, successive signs. Okay, first we should understand what the signs are. So this arc you divide it into n parts. So r sin theta is r theta, s is r theta. So js by n is the first part. I have not shown. This is some jth part. This is j plus 1 part. Cj is jth part. Cj plus 1 is j plus 1 part. You consider the midpoints also, and then you have an argument to show that the sign difference is proportional to the cosine at midpoint. So the second order sign difference is proportional to the sine itself. Second order sign difference. That is, in modern language, r sine n plus 1 theta minus r sine n theta, cube this first order sign difference, minus r sine n theta minus r sine n minus 1 theta. That is a second order sign, and that is proportional to r sine n theta. So this was basically our Aryabhatta's result, and giving better and better value for these coefficients will give you an immediate way of integrating this. So this is a difference equation. You have an exact coefficient here, you can integrate it to get sign tables. That is one way to get sign tables. That
no, wait a second. Second order difference equation is like but still
okay.
In terms of sign.
So this you call it as delta n plus 1. So delta n plus 1 minus delta n is proportional to r sine n. This is what I am calling as dn delta. So the second order sign differences are proportional to sine. So in analogy, this is similar to the second order differential equation. d squared sin x by dx squared is proportional to sin x, of course with a minus sign. What is the standard equation for a harmonic function? So Aryabhatta has it in the difference form, and he is immediately able to the coefficient, the better and better accuracy of the coefficient, you can numerically integrate it immediately to find out the sign table. So this is an extraordinary way of doing sign table. There is nothing to do with the Ptolemy's the kind of brute force method you use the Pythagoras theorem again and again to cut the overall angle into smaller and smaller angle, have a half angle formula and then use square roots. So Aryabhatta is doing nothing like that. He is doing a numerical integration on a difference equation. And in fact, historians have commented upon it that something like this was done in Europe by this man called Briggs, who is the originator of logarithms. He is around 1650, 1660. He suddenly comes up with this kind of a method. In fact, even historians wonder how did Briggs arrive at this kind of a numerical integration of sine. So, in Neelakanta's Aryabhatiya Bhashya, Neelakanta's Tantra, he does give this method and a good expression for this coefficient. Shankara gives even better expression for this coefficient so that you can integrate it and obtain values. So this is one way of doing sine table which Ram will tell you. Now Madhava went on to do it another way. He arrived at this infinite series. R sine is s minus s cube by 3 factorial, s 5 by 5 factorial, s 7 by 7 factorial, which is the modern one. So Yukti Bhasha and Yukti Deepika gives the derivation of this. What they use is equations like this. Repeatedly, using those equations repeatedly, coming over them, going to certain limits, they are able to derive this infinite series. And that is the derivation. Perhaps I will present the derivation to you tomorrow. So cosine series, again this is given in. This is but sine theta. If you have to, this is 1 minus r cos theta. So cosine series is also there. Say series for sine square x is also given. Now what Madhava does after this series is, he will immediately compute these coefficients, these portions, and give you as given constants. So that for any arc, because this sine function is going, cosine and sine functions, they are going like factorial 2n plus 1. They are very, very fast convergent. It is not like the Leibniz series. Right? N factorial is a very, very, it goes to infinity very fast. We know the Stirling's formula and all. So, even if you use 5-6 terms, you get accuracy of 10 decimal places per sine. So Madhava is giving 5 coefficients in the sine series, and that you can use to calculate the sine of any angle to fair amount of accuracy. So those coefficients, he has given it as a code: Vidvan, Tunna Balaha, Kavisha Nichayaha. So those are the codes. You use that and calculate. Sine of any angle can be. You don't need to do interpolation. You don't need to remember any tables. Then he has also used this series to give you the values of sine at those 24 points, which was the standard points of Indian astronomy, dividing 90 degrees into 3 degrees 45 minutes, 7 degrees 50 minutes, those 24 points. So those are called the Pindajyas. So that is also given in terms of Katapayadi by verses called Shreshtham Nama Varishtanam, etc., which is quoted in Neelakanta's Aryabhatiya Bhashya. So all this is introductory summary to what Ram will tell you. Now I will go to the 1 or 2 last points. So Neelakanta did a significant improvement on this velocity formula, Bhaskara and Modular. The position of a planet is actually given by sine inverse of a constant of sine of what is called the anomaly. So there is a sine inverse function involved, and you have to differentiate this. It is this m and alpha which depend upon time. For moon, both will depend. For the case of sun, only m is directly proportional to time. For the moon, the apogee is also moving slightly. Now, here we
will be linearly going.
It's linear. There is no complexity in differentiation. But that's also time dependent. So now he is giving this. Neelakanta attributes this formula. He gives this formula in terms of Sangraha just like that. In his Jyotirmimamsa, he says this verse is due to Damodara. So this verse might be arrived at, people might have thought about this problem and obtained this. So this is the square root of 1 minus x squared as derivative of sin inverse x. That is what is involved here. Later astronomer, this Achyuta Pisharati, he considers a different planetary model itself, where the planet's position is not given by sin inverse of sine, but is ratio of two functions. Achyuta Pisharati's time is 1570 to 1640 or something like that, and he has this formula for the derivative of the ratio of two functions. In a particular case, he is working out the derivative. He has the correct kind of derivative. So this instantaneous velocity is understood as a consequence of this differentiation by these people. So this is roughly up to 1600, the development of the work of Kerala school. After that, if this Karana Paddhati is a later book that has different kind of algorithms, it has some more infinite series, a few more, one or two different examples, but a very detailed treatment of approximation of a rational number by its continued fraction. It sort of takes that subject really to the logical conclusion, how best it can be done and how, what kind of techniques it uses it repeatedly in a very significant way in astronomy. And it has an improved Vakya system. It's telling you how to make a Vakya Karana, how to make a Karana text, how to do it. Then we have Sadratnamala. Sadratnamala has value of 5 to 17 places. Then it has an interesting algorithm for cube root, approximate one, right? So we have to see other Kerala texts to see how this calculus proceeded from here, if at all, to what extent. And are there texts in other areas? What has been published is only Vish told us about this 4 texts in 1835, and we are almost near getting all those 4 texts. Still Karna Paddhati has to come out, so we are almost near getting all these 4 texts analyzed. Now there may be further work on that. And the detailed nuances and all this, one has to restudy this text and go to it again and again. Professor Divakaran is trying to do that kind of a work, trying to see what do they understand in doing one, do they understand this operation better, that operation. Then comes the kind of question, how does it compare to how they did it in Europe and all that. So there are many issues that one could investigate, but it's a very interesting chapter in the development of Indian mathematics, calculus and Kerala. Thank you.